Hi. So in this video, we will go over the exact questions for gravitation. And as before, no, I've already worked out the questions, and no, we'll go over them in detail though. So let's start one after the other. Let's start with the first one. How does the force of gravitation between two objects change when the distance between them is reduced to half? So we know that, let's consider the two objects as A and B, and their mass is MA and MB. The distance is D. And we know that, for Newton's universal law of gravitation, we know the force between them to be, G times MA MB over D square. Now, if their distance is reduced by half, we'll replace, D by 2. So, which becomes like, they get closer. So, F prime, which is the new force, which becomes like G times MA MB over D squared times 4, right? Because the distance has come down twice. So it comes out to be, your F prime is 4 times the original force. So when the object comes closer, the force increases, and that's Newton's, that's based on Newton's, law of gravitation. Question 2. Gravitational force acts on all objects in proportion to their masses. Why then a heavy object does not fall faster than a light object? So two objects of different masses, MA and MB, and let's consider the mass of the Earth to be capital M, right? So if you really see here, for the first object, their force, the force between the first object A and the Earth is going to be G times the mass of the first object A times M by D squared, right? Now this force is nothing but the weight, right? The weight of that particular object as it falls on the Earth, and you know that we can replace that force by MA times G, right? The weight is nothing but mass times G. Now, if you replace that, then your these gets cancelled, and your gravitational constant becomes equal to the universal, the Earth's acceleration due to gravitation force is equal to G times the mass of the Earth over D squared. So G is independent, right? The acceleration due to Earth's gravitation force is independent of any object, right? And that is the reason why you don't have for all objects that are closer to the Earth, right? For all objects that are closer to the Earth, they will fall with the same. They would fall with the same. They'll fall with the same velocity. Primarily because the Earth is huge, and that the radius of the Earth itself is large when compared to the object that is falling from a certain meters above the Earth. So that's the reason. What is the magnitude of gravitational force between the Earth and a 1 kg object on its surface? Mass of the Earth is 6 times 10 power 24 kg, and the radius of the Earth is 6.4 into 10 power 6 meters. So we can apply the Newton's law of gravitation, considering the mass to be 1 kg of the object, and the mass of the Earth to be 6 into 10 power 24. D is the radius of the Earth. We can calculate the force, which is equal to the gravitational constant times the mass of the object times the mass of the Earth by the radius of the Earth squared. So when you equate that, it comes down to be approximately 10 newtons. Question number 4. The Earth and the Moon are attracted to each other by the gravitation force. Does the Earth attract the Moon with a force that is greater or smaller, or the same as the force with which the Moon attracts the Earth? Why? So Newton's law of gravitation calls out the net force between the two objects, right? It is actually the between two objects A and B. It is the force with which A attracts B, and it is also the force with which B attracts A. Both are the same, right? As we went through in the earlier thing, in the earlier video, when an apple falls on the Earth, it is the Earth that is attracting the apple, as well as it is the apple that is attracting the Earth, based on this formula, right? It is just that the apple moves because its mass is less towards the apple moves towards the Earth. So in this case, the force would be equal, with which it's the same. So the magnitude of the force would be the same, right, with which both the objects attract each other. If the moon attracts the Earth, why does the Earth not move towards the moon? We spoke about it, right? So the mass of the moon is less than the mass of the Earth. Hence, the moon accelerates towards the Earth, right? Just like how the Earth does not move towards the apple, right? Because the apple's mass is less, so the apple ends up moving towards the Earth. But the force is the same. The force with which the moon attracts the Earth and the Earth attracts the moon is the same. But just that the Earth doesn't move because its mass is relatively more. What happens to the force what happens to the force between two objects if the mass of one object is doubled? I think there are three scenarios here. Let's take one after the other. The scenario of the mass of one object is doubled. So let's consider the two objects to be A and B, and they are separated by distance d, right? So the force between them is equated to g times ma times mb by d squared. So when the mass of one of the objects is doubled, we know that let's consider ma is doubled to 2ma, which means that the net force, which is the new force F prime, will become 2 times the original force. So when the mass of one object is doubled, the force is also doubled. What happens when the distance between the objects is doubled and tripled, right? So in this case, when the distance is doubled, then your original d becomes 2d, which is 4d squared. The denominator becomes 4d squared, and this becomes 1/4 of the original force. So when the object's distance moves away, when is increased, because the distance is inversely proportional to the force will also decrease, and here it decreases by 1/4. Right. So what happens when it is tripled? When the distance is even further separated, then it becomes 1/9 of the original force if you apply the same logic. What happens when the mass of both the objects are doubled? So when both the objects are doubled, then ma is equated to 2ma, mb is equated to 2mb, which becomes like your new force becomes 4 times the original force, right? Because it is the mass of the objects are directly proportional to the force, so it increases. Question 7. What is the importance of the universal law of gravitation? It helped us explain many things, right? Main thing is, it explained the gravitational force of the Earth. We were able to derive 9.8 meters per second as the acceleration due to Earth's gravity. We were also able to explain the force between two objects in general, any two objects. That was the main value. We were also able to explain the motion of different planets. Right, how the Earth revolves around the Sun, as well as how the Moon revolves around the Earth, and all that. And we also know that this is also helping us in terms of sending satellites. Satellites operate like the Moon, right? They are right at the point outside of Earth's gravity, so that they constantly like the Moon, they constantly fall on the Earth, and they end up revolving around the Earth. And of course, they help us explain why there are high tides and low tides, because when we're based on the position of the moon, right? And these are all the primary importance of the universal law of gravitation. We were able to explain and understand all of these because of Newton's universal law of gravitation only. What is acceleration of free fall? Acceleration of free fall is the acceleration encountered by an object that is under the influence of Earth's gravitational force, and we derived that, and it is denoted by the letter small g, and we figured out that it is approximately equal to 9.8 meters per second squared, and we derived that based on the Newton's universal gravitational constant and the mass of the Earth and the radius of the Earth. What do we call the gravitational force between the Earth and an object? We call it the force of gravity, right? Amit buys a few grams of gold at the pole as per instructions of one of his friends. He hands over the same when he meets him in the equator. Will the friend agree with the weight of the gold bought? If not, why? So the hint here is that the value of the gravity, right, the acceleration due to gravity is greater at the poles as compared to the equator. Okay, so that is a hint here. So let's consider it this way. The gravity at the equator, let's consider it to be GE, and let's consider the gravity at the pole to be GP. and based on the hint, we see that GP is greater than GE, right? So mass of the gold is M. So when they have let's consider the mass of the gold to be M, and since Amit has bought them at the poles, so the weight of the same gold in the pole would be mgp, and the weight of the same when it is measured in the equator would be mge, right? So when a friend is measuring this in the equator, the same mass would appear less because the weight as measured in the equator will appear less as compared to what was measured on the poles. So his friend will not agree because the weight of the gold will measure less on the equator. Why will a sheet of paper fall slower than the one that is crumpled into a ball, right? Why will the sheet of paper fall slower? So we saw in our example that whenever an object is dropped, there is a resistance from the air, right? As long as it is not dropped in a perfectly vacuum place, there will be resistance from the medium. When it is dropped in air, the air will offer some resistance. When it is dropped in water, the water will offer some resistance, right? And that resistance will always be in the perpendicular direction, the upward direction. When you drop a sheet of paper, that resistance will act on different parts of that sheet of paper. So the surface area of that paper is bigger when it is not crumpled. When it is crumpled, the surface area becomes smaller. So the resistance acts on a smaller area, right? But when the paper is not crumpled, it is large. It is thin and large, so the air resistance will apply on every part of that paper. So the resistance will be higher, and that's why it takes longer time to fall as compared to the ball, right? Gravitational force on the surface of the moon is only 1/6 as strong as the gravitational force on the Earth. What is the weight in newtons of a 10 kg object in the moon and on the Earth? So the mass of the object is 10 kgs. Let's consider Ge to be the gravitational force, the acceleration due to gravitational force on the Earth, and Gm to be the gravitational force on the moon. And we know that the acceleration due to moon's gravitational force is 1/6 of Ge, right? So it is going to be this. So weight of the object on the moon is going to be m times Gm, right? And we know that Gm is equal to the Earth's gravity over 6. So which becomes like, the weight of the object on the moon is 10 over 6 GE, and GE, we know it is 9.8. So it approximately comes down to, 6.3 kg meters per second square. So this is the weight of the object, the weight of the object this is the weight of the object in the moon, and this is the let me see. So which one is 10 kg object on the moon? And okay, so we haven't described the one for the one on the Earth. So yeah, so on the Earth it is going to be 10 times 10 times 9.8. So it is likely going to be 98 kgs, and in the moon it's going to be 16.3 kg meters per second square. Yeah. On the Earth it's going to be actually 98 kg meters per second square. Yeah. A ball is thrown vertically upwards with a velocity of 49 meters per second. Calculate the maximum height to which it rises, the total time it takes to return to the surface of the Earth. So the ball is thrown it's thrown vertically up with a velocity of 49. So the initial velocity with which it was thrown is 49 meters per second. What is the maximum height? At the maximum height, the ball's velocity would become 0, right? That's when it will change its direction. And we know that the acceleration should be 9.8 meters per second, but in the opposite direction, right? It is 9.8 when it is falling down, But since the ball is moving up, it has to be minus 9.8 meters per second squared. So we know from the third equation of motion, we can use that. 2as is equal to v squared minus u squared. Now with this, if you are able to substitute the values of v, u and a, you can get the distance traveled. So with that, you will find that the distance traveled by that object is 122.5 meters. So that is the maximum height that the object would have moved up. Second question, the total time it takes to return to the surface of the Earth. So in this case also we can use the probably the first equation, which is v is equal to u plus at. So when you substitute the values for v, u and a, you will find that t becomes down to be 5 seconds. So this is only one way. So this 5 seconds is for the object to reach the maximum height, and it will take another 5 seconds to reach the bottom. So the total time taken is going to be 10 seconds. A stone is released from the top of the tower of height 9.6 meters. Calculate its final velocity just before touching the ground. So the height of the tower is 19.6 meters. So yes, has to be 19.6 meters. The stone was dropped, released, right? So which means that the initial velocity was 0. The question is, what is the final velocity, which is v? We know that since the stone is on free fall, we know its acceleration is going to be 9.8 meters per second. So with this, you can apply the third law of motion, which is 2as is equal to v squared minus u squared, and with this you can find out v, which comes down to be 19.6 meters per second. So we'll stop here, and we'll complete the rest of the questions in another video.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share and subscribe this with your friends. Thank you.